Welcome to Copernicus AI Frontiers of Science. I'm Bella, and today we're diving deep into quantum sensing and metrology. Brian, with all the buzz around quantum technologies, what makes the recent advancements in quantum sensing truly revolutionary?
Thanks, Bella. It's a pleasure to be here. The revolution in quantum sensing stems from its potential to surpass classical limits in measurement precision. We're not just talking about incremental improvements. We're talking about orders of magnitude. For instance, consider the work by Luis Bugallo and colleagues in their 2024 paper, Private and Robust States for Distributed Quantum Sensing. They explore how to estimate multiple parameters encoded in spatially separated probes. This is a game changer because it allows us to build distributed sensor networks that are incredibly sensitive and resilient.
Distributed sensing sounds powerful. Can you give us a concrete example of where this kind of sensitivity could be applied?
Absolutely. Think about environmental monitoring. Imagine a network of quantum sensors spread across a large area, each measuring minute changes in temperature, pressure, or magnetic fields. By combining the data from these sensors using quantum correlations, we could detect subtle environmental changes that would be impossible to detect with classical sensors. This could be crucial for early warning systems for natural disasters or for monitoring the impact of climate change.
That's a compelling application, but quantum systems are notoriously susceptible to noise. How do researchers address this challenge, especially in what's often called the noisy intermediate-scale quantum or NISQ era?
That's a critical point, Bella. The NISQ era presents significant hurdles. Lin Jiao and their team address this directly in their 2023 paper, Quantum Metrology in the Noisy Intermediate-Scale Quantum Era. They investigate how to realize high-precision measurements despite the limitations of current quantum devices. Their work explores using quantum features like entanglement and squeezing to push beyond classical limits, even with noisy qubits. The link is in the description if anyone wants to dive into the technical details.
So, even with imperfect quantum computers, we can still achieve significant improvements in measurement precision?
Precisely. It's about clever engineering and designing quantum measurement protocols that are robust to noise. For example, researchers are exploring error-correcting codes specifically tailored for quantum metrology. They are also developing hybrid quantum classical algorithms, where the quantum computer performs the core measurement, and the classical computer handles the error correction and data analysis.
You mentioned entanglement and squeezing. For our listeners who might not be familiar with those terms, could you briefly explain how they enhance measurement precision?
Certainly. Entanglement is when two or more quantum particles become linked, even if they're separated by vast distances. Measuring the state of one particle instantly tells you something about the state of the other. Squeezing, on the other hand, involves reducing the uncertainty in one variable at the expense of increasing the uncertainty in another. By carefully entangling and squeezing quantum states, we can create sensors that are much more sensitive to specific signals.
This almost sounds like science fiction. Are there any potential applications of quantum sensing beyond environmental monitoring? What about fundamental physics?
Absolutely. Quantum sensing is poised to revolutionize our understanding of the universe. Think about detecting gravitational waves. Thiago Guerrero and colleagues explore quantum signatures in nonlinear gravitational waves in their 2021 paper. They propose using quantum sensors to detect subtle quantum effects in gravitational waves, potentially opening a new window into the nature of gravity itself. The paper is available for free on Arxiv, link in the description. This could allow us to verify the quantum nature of gravity, which is one of the biggest open questions in physics.
So, quantum sensors could help us bridge the gap between general relativity and quantum mechanics?
That's the hope. By detecting quantum signatures in gravitational waves, we could gain valuable insights into the behavior of space-time at the quantum level. This could lead to a deeper understanding of black holes, the early universe, and the fundamental laws of nature.
What about more down-to-earth applications? Are there any military or security applications of quantum sensing?
Indeed. Michal Krelina's 2021 report, Quantum Technology for Military Applications, discusses the potential of quantum sensors for various military purposes. Quantum gravimeters could be used for navigation without GPS, quantum magnetometers for detecting submarines, and quantum clocks for secure communication. However, it's important to note that these are dual-use technologies, and their deployment raises ethical considerations that need to be carefully addressed.
Ethical considerations are definitely important. What about the energy demands of these quantum technologies? Are they energy-intensive?
That's a really important question, and it's an area where more research is definitely needed. As AOFEV points out in their 2021 paper, quantum technologies need a quantum energy initiative. The energy cost of operating quantum devices can be significant. Developing energy-efficient quantum technologies is crucial for their long-term sustainability.
Brian, this has been an incredibly insightful overview of quantum sensing and metrology. It's clear that these technologies have the potential to transform not only science and technology, but also our understanding of the universe itself. What would you say is the most exciting frontier in this field right now?
For me, the most exciting frontier is the intersection of quantum sensing with other areas of physics, like quantum field theory and cosmology. The potential to use quantum sensors to probe fundamental questions about the nature of reality is truly mind-boggling.
Thank you, Brian, for breaking down this groundbreaking research. It's inspiring to see how quantum technologies are pushing the boundaries of what's possible. It seems we're on the cusp of a new era of scientific discovery, driven by the power of quantum sensing.
My pleasure, Bella. The future of quantum sensing is bright, and I'm excited to see what new discoveries await us.